So, what is a derivative conceptually? Well, if you just look at the graph purely, the derivative is simply the slope of the graph, the slope of the line tangent to the graph at any given point, okay? So, say this is point A, right? So, this is the derivative of f at A, all right? So, what we would call this f prime of A, okay? So the derivative would be f prime of x, and if you want to evaluate the derivative at x equals a, you would write f prime of a, and f prime of a equals the slope of this graph, the slope of this line, which is tangent to the graph, okay? This would also be dy over dx, the at x equals a, okay? dy dx and f prime of x mean the same thing. There's different ways to notate it. The derivative allows us to there's a lot of useful applications for derivatives, especially when you're dealing with the rates of change and stuff. Like, for example, if you wanted to find the derivative of distance, that you would get speed, and if you want to find the derivative of speed, you would get acceleration. So these are some this is just basically what a derivative is conceptually. So now exactly how would you approach finding the slope of a tangent line at any given point? Well, what we did is we first start with the slope of the secant line. We know how to calculate that, right? Let's say this is a, and then let's say this is a plus h, right? And you want to find the slope of the line at x equals a. Then what we would do is we could first find the slope of the secant line and see how the slope of the line behaves as we close this gap, all right? Because the tighter this gap becomes, the more accurate our approximation of the slope of the line becomes, right? So what does this remind you of? This is this something that we've seen before? Well, this is a limit. Essentially, what this is telling us is the limit as h approaches 0 of f of x plus h minus f of x divided by h, okay? This is the limit definition of the derivative, okay? So, remember, this is... Oh, I'm so sorry. This is not f of x. It's supposed to be f of a. Okay? So, remember, this is a of h, right? And we want to evaluate the delta y, which is the change in y, versus the change in x. Okay, so the change in y is f of a plus h minus f of a, and then delta x you see is just h. Okay, so now when you let h approach 0, then we're going to get points. We're going to essentially close this gap, and the slope of the tangent line, or the slope of the secant line, slowly approaches the slope of the tangent line. So this is what the limit definition of the derivative is. Okay, so another way we can look at a derivative is to graph 2 points. We have the point A, f of a, and we have the point x, f of x. Okay? Now, if we draw a secant line between both of these points, what do we have? Well, the slope of the line would be f of x minus f of a divided by x minus a, okay? And now we can sort of approximate the slope of the line that's tangent to the graph at, x equals a. If we let x slowly get closer and closer to a, okay? So we're doing the same thing as we did previously, except now, instead of letting h approach 0, we're letting x approach a, and then obviously we want to evaluate the slope, so we're going to write f of x minus f of a divided by x minus a, and that equals the derivative of f of x at x equals a. So we just write that as f prime of a. So that's also another way. So we have our first definition, which is the limit as h approaches 0 of f of a plus h minus f of a divided by h. And then we also have our new definition of the derivative. And both these are equal to f prime of a. Okay? Now, let's look at how we would use the limit definition of the derivative to evaluate some derivatives, okay? So if I have the function f of x equals x squared, and I want to evaluate the derivative of f at x equals 6, I would write this as f prime of 6, okay? F prime of 6 equals, well, there's two ways you could write it. We could write it as the limit as x approaches 6 of f of x minus f of 6 divided by x minus 6, or we could write that as the limit as h approaches 0 of f of 6 plus h minus f of 6 divided by h. Okay, these are the two different ways you could write it. Okay, so you can evaluate either one of those limits and you'd get the same value, which is the derivative of f at 6. Now I'm going to solve it using both ways, okay? So let's go do it. So I'm going to first solve using this way, okay? So let's do this. So now this is equal to the limit as x approaches 6 of, what is f(x)? F(x) is x squared. Fx squared minus, 6 squared, which is 36, divided by x minus 6, okay? Do you know how to evaluate this limit? Well, I mean, we learned that in the last unit, so that's just the same as the limit as x approaches 6 of x plus 6, x minus 6 divided by x minus 6. Okay, you cancel these two out. It equals the limit as x approaches 6 of x plus 6, which equals 12, okay? So here we just proved that the derivative of x squared at x equals 6 equals 12. Okay? Now, let's do the same thing using the other definition of the derivative. We should get the same value 12, but it's important to be familiar with using both of the limit definition of the derivative to evaluate them, okay? It's important to master how to evaluate using the limit definition before we can get into some shortcuts we have for finding derivatives, okay? Now, let's evaluate the limit using the other method, okay? The limit as h approaches 0 of f of 6 plus h minus f of 6 divided by h, okay? That's equal to the limit as h approaches 0 of 6 plus h squared minus 6 squared divided by h, okay? Now, when we evaluate that, we get the limit, or when we simplify that, we get the limit as h approaches 0 of 6 squared plus 2 times 6h plus 6 squared plus 8 squared minus 6 squared divided by h, okay? Because that's what happens when you expand 6 plus 8 squared. We cancel these two out, so then we get 2 times 6, which is 12. We get the limit as h approaches 0 of 12h plus h squared divided by h, okay? Now we can just cancel out the h's, and then we get the limit as h approaches 0 of 12 plus h, which is equals 12, okay? And that's what we got with the other result, okay? So that's how we can use both of the definition of the derivatives, the limit definition of the derivatives, to set up a limit and then solve for the instantaneous rate of change of any function at any point, okay?